Okay. Hi, everybody. Welcome to the our next round of fellowship presentations. Just let everybody know that we're recording the meetings so that people can view them later. So just give you a heads up. Anyway, the first one we're going to start off with is Erik. Erik?
Hi. Okay. So, hi everyone, and thanks for coming here today. So I will start off with the first project for today, which is I've been working with evaluating the ZFP compression algorithm, focusing on the NanoAOD format at CMS. So my name is Erik Wallin, and I'm a master student in physics at Lund University in Sweden. And I have been supervised by Oksana Shidura and Brian Bockelman. I'll start off by introducing ZFP with a quote. So ZFP is a BSD licensed open source library for compressing floating point arrays with a focus for supporting high throughput read and write random access. ZFP was designed to achieve high compression ratios and therefore uses lossy but optionally error-bounded compression. Bit-for-bit lossless compression of integer and floating point arrays is also supported. ZFP is often more accurate and faster than other lossy compressors, especially in its OpenMP and CUDA multi-threaded modes. Okay, so what this means is, so ZFP is a lossy compression algorithm, but it is optionally lossless. Its goal is to support high throughput read and write random access speeds and high compression speeds. And you can read all about it here. So at CMS today, I will explain how the compression is done. So for floating point arrays, it has two steps. First, the mantissas of every float are first truncated to some user-specified position. So we lower the precision of floating points a bit. And this is done in a library called libminifloat, which I will abbreviate as LMF on figures. These float arrays are then followed by the usual lossless compression methods that are available in root right now. And these lossless compression methods, their compression improves significantly because we have done this float truncation step before. So what I will be doing, I will be seeing how this new ZFP algorithm compares to the lossless methods available in root today, which are LZMA, ZLib, LZ4, and ZStandard. So I have done a pure Python implementation for this, and for simplicity, I'm only working on flat data, so no jagged arrays. But one should, of course, do a proper root implementation to get true real numbers. Okay, so what we want to compare is I will use ZFP compression on data that is not compressed by this libminifloat float truncation, but the other ones, LZMA, LZ4, ZLib, and ZStandard, will be compressing data that is already compressed by libminifloat, as is the case at CMS today. So I won't have time to show very many figures, but I will explain how to read them, and there are several more of them in the slides if you want to have a read later. So here in this figure we compare the compression ratio on the y-axis to different methods. So in the purple dashed line we see the compression ratio for ZFP. Below that we see in dashed green we see LZMA and the others below. So we see that ZFP is the winner here. So ZFP is a lossy algorithm. So but we can specify the precision for this lossiness, and this what I call the CMS SW precision is the same precision as the floats would lose in the lib mini float step. So there is no extra loss in accuracy from ZFP compared to lib mini float. In these solid lines, we see ZFP compression ratio for the same data set, but for different precisions on the x-axis. So we see that it performs poorly when doing near lossless compression, but when the precision is very low, we get very high compression ratios on the top left. We also want to compare compression speed in megabytes per second, and they are shown here. So ZFP is often faster than the other methods. It does sometimes lose to Z-standard and LT4 and ZLib in their fast settings, but for the other methods in their maximum compression settings, ZFP is often the winner. And most notably, ZFP seems to nearly always have been a case that it is faster than LCMA. So we can also plot the compression speed versus the compression ratio in a plot like this. So, and in a plot such as this, we would want to approach the top right corner with high compression speed and compression ratio, but one has to choose between those two. Here we see another data set, the electron NG-error, and in this dash line we see that ZFP performs very poorly for this data set, but it seems to be a feature that if ZFP is followed by LZMA or Z-standard, then the results can be somewhat salvaged. So the chaining of ZFP with some other lossless method is important. So here we have the same speed versus compression ratio plot for this NG-error dataset. And one feature of ZFP seems to be that the compression speed is kind of constant, or it's independent of the tolerance to a high degree. So we can often get high compression speeds for some dataset, both with low tolerances and high tolerances. Okay. Here we take a much closer look on comparing the chaining of compression methods. So here we have ZFP followed by LZMA in purple for a bunch of different branches in our dataset. And as green dots, we have lib mini float followed by LZMA. So a very curious feature here is that if we do LZMA on data that is compressed by ZFP, then the compression speed increases significantly. We see that very clear here also. So we plot the compression speed versus compression ratio, and the speeds for LZMA compression is clearly faster when it's preceded by ZFP rather than when it's preceded by lib mini float. So in total, if we can see that ZFP's compression ratio can outperform other methods, but it does not do this consistently. Actually, when working with near lossless precision, ZFP can actually yield larger file sizes than the uncompressed one. And we see that poor results from ZFP can be somewhat saved if followed by LZMA or Z-standard. If you want to try and estimate the compression for a whole file. We have here we have an NAOD with 65 megabytes of data. We compress all float branches with ZFP and then LTMA, and we compress non-float branches with LZMA, which gives us goes down to 80 megabytes. If we would instead do just libmini float and LTMA on all branches, it will go to very close to 50 megabytes. So for this data set, ZFP and LTMA seems to perform slightly worse than libmini float and LTMA, but it is an improvement in 12% of the branches, which is worth remembering. So what positive things can we say about ZFP? So in this, at least in this Python implementation, ZFP is faster than LZMA and speeds up an LTMA compression that follows it. We often have a slightly lower compression ratio than LZMA, but the important note is that we can use ZFP selectively on data sets or branches in the data where ZFP is more useful. And this is a reasonable thing to do because we already use it selectively only on branches where we have floats and so on. So the outlook from this would be to do proper tests in root to get real measurements, proper implementation. It would be nice to explore in further the chaining of different compression methods. For example, ZFP followed by other lossless ones. And maybe there's a golden combination of them. And it would be nice to do a more qualitative analysis of what causes ZFP to perform well or to be in some way be able to predict when it performs poorly. Okay, thank you. So we can move on to questions.
Maybe I'll go. So you were saying that one of the outcomes of this was that ZFP should be applied selectively. Do you know something about the data in the branches that that respond favorably? I mean, is there something a priori about the data that will tell you that ZFP is going to perform well versus?
That's like the whole problems of trying to predict when a compression method will be good or will be bad. So no, I sadly don't have any good indicators of when it will be good. But if you have similar files with similar physics, then you can check for one of them and apply that for the other ones. So if if some physical variables perform well in most cases, then you can use those ZFP on that data in other cases.
Have you seen cases where it performs well on a particular branch, like I don't know, electron PT in one data sample, but it performs poorly on that same branch in another data sample?
Not that I've thought about too much. No, I can't give you a conclusive answer for that. That would have to be looked at.
I think another thing to add is actually that we kind of get only one data sample. So all this evaluation we did on the bunch of files that Erik was kind of converting from AOD to mini AOD and then NanoAOD. So but it's very interesting in the terms of that it's not the first time that we see this. And there was another GSOC student that he was working on different compression algorithms, and there is something into maybe to investigate a bit more in the terms of to check out the patterns that we have in distributions, for example. And some of them are actually showing incredible results in both cases, in Erik's case and in other GSOC student. But for some of them, they're behaving poorly. And Gordon, if you're interested, there is, I think, distribution in backup. So if you will notice something tricky, just tell us.
Sorry, there's a distribution in the CAP? I didn't get that.
In backup, if you check the slides backup, there is distributions of for example, electron mass or electron, which I think Erik, you
We have them
mentioned.
at the end.
Yeah. So you could see, like, for example, for electron mass, it was like perfect, like really perfect compression, while for electron energy, it didn't like work well. And yeah, so it's something that I think we need to start to look. It's particular investigation of compression per branches and per types.
Yeah, so the main author of SFP, Peter Lindström, he has a few articles on like on just these metrics of like predictability and like bounds on the compression ratio and so on, but they aren't very practically useful results, sadly.
Anyway, I would like to add, thank you so much, Erik. It was a wonderful summer. I really enjoyed working with you.
Thank you as well. It was very nice.
Okay.
Thanks.
Thank you, Erik. That was
Thank you.
thank you. Thanks everyone for the questions. Moving along. Next up is Vladimir.
Yeah. I'll share my screen.
Sounds good.
All right. Can everyone see that?
I can see it.
Okay. I'll just begin then. Okay. Oh no. Okay. So I worked on Recast workflow, improving Recast workflow as my summer fellowship project, and I'm based in the University of Washington Computer Science Department. So my project is essentially a Python package that helps you quickly build workflows for testing truth level interpretations of models. And to better explain my work, it requires a bit more context. So I'll go a bit more into that. So a typical experiment I would see is where we just generate data, according to a model with some parameters, select some interesting data, and then run some statistical analysis on that. And that's a pretty common process, and that can be done by hand. But the idea behind Yadage is we can use YAML files to describe this whole process. That way Yadage can run it for us instead. So it would be one command instead of having to go through and run each of these individual programs one at a time. And this is, after you finish building your workflow, it's a much faster process to iterate over your model. And the idea is we can do this for truth level reinterpretations, which are faster to run and simpler to develop than running a whole full simulation. So you can quickly check results to see if this is a promising area of study, what you're looking at. And so what Recast workflow does is it abstracts that experiment to 3 different steps: generation, selection, and statistics. And you have options for tools for each step, and you can pick which ones you want to use. And it will build the workflow file for you, which often tends to be very long. And so how does it actually work internally? Recast workflow has an idea of all the input and output files between each step, and it uses that to build this kind of dependency graph on which processes require which inputs and which processes give which outputs. And what's nice is that Docker images encapsulate each step. So when you go to run it using Yadage, there's no assumptions about the environment you're on. This will work on Windows and Mac, and you don't have to run any sort of shell script to set it up. And yeah, it essentially generates these step combinations for which the user can pick from. Okay, so now on to what I did. So I think the first thing I did was clean up the project and organize it a bit, because the way it was working before, it was not actually a Python package. Rather, it was just a bunch of scripts which you would put inside your Python path variable so you can import them. But when you change it to a package, a lot of new opportunities arise, and it's just much cleaner code. And a consequence of this actually is that the command line interface can now be used interchangeably with Python. So you can use Python if you want to do some more complex operations on the workflow after you're done, or you can just use Bash to quickly generate these workflows. And next up, so I created a PyHF Docker image. This just contains a bunch of Python dependencies for PyHF. And I think a previous talk talked about what PyHF is, but we essentially use it as another statistics option, statistics tool option. And when I say sub workflow, this is just defining the YADage we use, the YAML we use to represent this specific step. And it also includes a new file interface called the PyHF workspace. So this is what PyHF actually takes as input, and then you would apply your script to it, and you would get some outputs. And you can try it out. It's published on Docker. So even if you're not interested in using Recast-workflow, if you ever need a Docker image for PyHF, you can quickly grab one from here. Okay, and then the same process was done for MAT analysis, and MAT analysis takes a HEP-MC as input, and then it also takes your run card, and this just specifies a bunch of commands you want to run on it. In our case, we were more interested in the recast feature of MAT analysis 5, so we added another recast card. And essentially what this allows you to do is you go through the file and you just set to true which analysis you want to run, and these are previous analysis people did. So you can quite easily reproduce other people's work from other papers by just getting their analysis number, which is in the MAT analysis 5 database. It's written on their website somewhere. And you can just quickly set that to true and try it out. And MAT analysis 5 actually can also do selection, which is interesting. So in here, you can also do selection, and that simplifies the number of steps you have to run. And once again, even if you don't use this, this is a very useful Docker image for you to have. And then this is a part where the majority of Python code was actually made. So right now, the way this would work is you can only run the workflow for a single point in terms of parameters, right? So if I have two parameters, X and Y, I would only be able to run it for one value of X and Y. So I just added some features which can help you actually build what are known as multi-stage workflows in YADage. And these can be quite complex, but for our purposes, just takes the single stage workflow and duplicates it so that it runs for every single pair of parameters you have. It's not necessarily a pair, but set of parameters. And this also kind of ties in with Rihanna. Rihanna allows you to take these multi-stage workflows and it parallelizes them so that only one workflow is running on one computer in the Rihanna cluster, and then another workflow is running on the Rihanna cluster at the same time on a different computer. And so this can lead to a very large speed up in how fast we can actually run it. And I believe CERN has access to Rihanna. And so this just builds the extra file you need to submit a Rihanna job. Yeah, and there's some extra utility functions here where you're dealing with large amounts of files. Theoretically, these can all be replaced with just simple bash commands if you understand a little bit about bash scripting. But these make it just pretty easy to grab your results once you're done. And then this is the actual part where I published the Recast-workflow version 1. And so this is now completely public. It's installable through pip. And there's tutorials, there's documentation, which I recommend you read through if you want to know a bit more about the internals. And yeah, this is all public on readthedocs.io and GitHub and other stuff. And then Alex, one of my mentors, was actually putting together a boot camp. And what we realized is, I realized some of the code isn't actually Windows friendly because of the way slashes and backslashes operate. I just never tested it on Windows. So to fix this, I quickly put together a Docker image for Recast-workflow called Recast/workflow. And this just comes pre-installed with Recast-workflow, so you don't actually have to run the one command, which you need to install it. But it has some other stuff as well, which can be useful. And this is mostly for Windows users who don't really, can't really use Recast-workflow on their normal computer environment. And to actually run the workflows, you do need to, because Yadage requires, runs Docker containers, you would actually have to mount your socket, I believe, to recursively run these Docker containers. That way you can actually run the workflows. But if you're just interested in grabbing the workflows off of Recast-workflow and then running them on your actual computer, on your Windows computer, then that could be fine. It'll just be less convenient. And so this is just links to all of my work, pretty much. These are the final products. A lot of the intermediary steps, for example, for meta-analysis 5, there was a lot of time I spent trying to reproduce a specific analysis. That's also on my GitHub, and I can send it over to you if you're interested. But this is essentially all the final products. And this 40-minute video explanation, it kind of goes deeper into how Recast-workflow actually works and all of its features. The first 10 minutes, the idea is this presentation can explain it from scratch. So the first 10 minutes just explain Docker, which may be less interesting to people who already understand that. And I think, you know, even if you don't use Recast-workflow, these Docker images are still going to be very useful if you're trying to develop in a standard environment as a team. Because somebody's working on Mac, somebody's working on Linux, and somebody's working on Windows. Docker can't handle all that. Okay, and as for the summary, so all the proposal goals are actually met. This is what I initially set out to do, and that's pretty much what got done. And yeah, there are a few things which can be tuned up, but some ideas for future work is, first of all, the way the PyHF sub-workflow works right now is it takes a PyHF workspace as input, but that doesn't really connect to any of the other previous steps. The other previous steps all output HEPMCs or .LHCs, which makes it difficult for PyHF to interpret that. And I think one of my other mentors, Lucas, was actually working on creating a converter, or he was interested in doing that. So we can add that as well to enable PyHF to be connected to the other sub-workflows. And then as well as just create a default Python script, just like a default analysis, which outputs confidence limits or some other interesting statistics. That way you don't have to write your own every time. And there can be some code optimization for the dependency graph. Traversal, where we're generating the combinations. There are a few inefficient parts, and it makes an assumption about that there's no loops in our graph. Essentially, there's no cycles. And just some more tests to increase the code reliability, code coverage. And that's it. Any questions?
Just wanted to say that looks like a huge amount of work, very nicely done. And I don't know if it's you or Rob, but if someone could make sure to get your slides posted, that would be great now. Because yeah, there are some links that you had in there that I would love to go check out, and having them uploaded would be fantastic.
Yeah, Gordon, did you know you were actually my Physics 121 professor? Did you know that?
No, I did not.
I saw you in this meeting and I was like, oh, it's come full circle. Yeah.
That's awesome. That's awesome.
It's awesome.
Well, congratulations. You've clearly, despite my teaching, have done very well.
Where is the edit button? Usually there's like a add resources button here.
If you can't do it, Vladimir, just send me the link to the PDF and I can upload it too. So
okay,
yeah,
great.
The reason is you weren't added as an author.
Yeah,
I think I can quickly fix that.
okay. Any other questions? Thank you, Vladimir. That was a good presentation. Up next is Thomas. You're up next.
Yep. Just gonna share my screen here. I believe you'll be able to see it now.
Yep, can see it.
Awesome. Okay. So my name's Tommy Shearer. I was an IRIS-HEP fellow for the summer. I'm an undergraduate at the University of Michigan, working under Sean McKee. And my fellowship project was to improve the OSG-LHC network metrics user interfaces. And just some brief background, I submitted my proposal under the name Improving the User Interface to the OSG-LHC network metrics. And so my initial ideas were just to work on dashboards and better ways to show the data that's being stored on the Atlas Midwest Tier 2, just because some of the data was very broad. But as I worked on the project, I was introduced to other opportunities to allow users to easily navigate to the dashboards and information that they might be interested in, and that was the OSG Toolkit info page, which I'll get to later in the presentation. And so the initial project plans, like I kind of mentioned, were to use the data being stored on the Elasticsearch instance at the Midwest Tier 2. Since I had a lot of experience with the Elk Stack at the Atlas Great Lakes Tier 2, just because a lot of the dashboards were showing very broad data. It was only within a specific time frame. And so I wanted to create different dashboards that would allow users to answer questions or specific problems on one page instead of having to navigate through a few general pages of information. And so all of the data that they'd be looking for a specific problem would then just be in one neat area instead of having to find it themselves. And so some initial progress, I started creating very rough dashboards just to kind of feel out the waters, but mostly the first week or two was introducing myself to various communities to see if there were any specific problems or use cases that they'd like to see discovered. So that was US Atlas facilities, the OSG facilities, the SAN group. And so as I kept working, I kept presenting the progress that I've made to these groups, as well as the group of people I worked with, including Sean. We had weekly meetings. And this is where I was kind of introduced to the OSG Toolkit info page, where I had my initial ideas of creating a system that would use this website as a way to be a central location for the dashboards. And so this image here is what the OSG Toolkit info page used to look like. As you can see, it was a little outdated, a little bland. And so I wanted to not only revamp all the graphics on this, as well as create dashboards, but also add features that would help users easily identify information that they might not know. And so more progress on the dashboards. I came across the main use case on the dashboards that I had explored for most of the summer, which is helping site administrators solve any general problems that they're having with their sites, even if they don't know a lot about the naming schemes or the definitions of what the data being stored at the Midwest Tier 2 is. And so with this goal in mind, I started making some real dashboards, started laying the foundation so that the users could access all type of data that they need. And so when I was creating these first dashboards, the initial the visualizations, the way of displaying data that I was making weren't very useful. And so as I kept presenting the progress that I was working on and presenting them to the groups that I meet with every week, they became more user-friendly, and it directs someone to information that they don't necessarily know what they're looking for. And so I came up with a scheme where the dashboards start very general and then get much more specific as the user progresses down the page. And there's a link, but it's also all public. You can look at all the dashboards via Kibana for the Midwest Tier 2. And so for this example, I'm going to use the Atlas Great Lakes Tier 2 as an example site. I pasted the filter you need to ensure that you can see all the information related to the Atlas Tier 2, both as a source and destination. And keep in mind that that's kind of complicated, and that's also another one of the motivations for the OSG Toolkit info page, which I'll get at later. But this is just the top of most dashboards. It allows users to go in between different types of information based on what the site may be. It allows users to select the source or the destination sites they're interested in. And so after they selected their site, You get to general averages between different sites based on what information you're looking at. For this PowerPoint, I used throughput as an example. And so the two on the left show the top 40 largest and smallest values for average throughput for the sites as a source. And then on the right, it's the same thing as a destination. And because we're looking at the Atlas Great Lakes Tier 2, all of the sites on the left are related to the Atlas Great Lakes Tier 2 when the AGLT2 is a destination. And so all of the ones on the left are the corresponding sources, and then vice versa for the destinations. And so because we're looking at throughput, you'd kind of be more interested in the top 40 smallest values, just because the smaller amount of throughput means you're going to have less data being transmitted. And so maybe you're interested in a specific site that you find and want to identify. So you'd be able to select those values if you'd like. But then as you scroll down, your information gets more specific. So like I mentioned, those graphs above were averages. But I started to notice that even though they have a pretty good average, for example, the AGLT2, the Atlas Great Lakes Tier 2 as a source site, and the Midwest Tier 2 as a destination site, they average about 3.4 gigabits per second. But I noticed that there was a lot of variance between the data. And so what I wanted to do is then create ways to identify if there's a lot of variance. So for that example, you can notice that there's a maximum throughput of 4.6 gigabits per second, but it has a minimum throughput of 1.9 gigabits per second. And so you may have a pretty good average in comparison to other site pairs, but it doesn't mean it's necessarily having good results all the time and having good performance all the time. And so from here, you only have two sites. You don't necessarily know what's going on. And so what I've done now is created looking between hosts that are being at each site and then the IPs that correspond. And so as you scroll down the page and identify, two sites that you're interested in, some variance in the data that you might be interested in that may be causing problems on your site, you now be able to have a breakdown of what hosts or IPs are specifically causing that variance. And so on these screenshots, you can see that, the top hosts for the source and destination are having a very large throughput, whereas the ones on the bottom are having a slightly lower throughput. And so you may be more interested in, now you've identified which hosts are having the lower throughput values, and maybe then the site administrators or whoever's having issues with their sites and maybe looking as to reasons why. Now they know specifically which hosts may be causing those lower and less optimal values. And so maybe, instead of knowing you're having a problem between one site and another site, you'd be able to identify exactly where that problem may be happening. And so after you maybe identified where that problem is happening, I've included previews of related data. So for throughput, related data is packet loss and retransmits. And so I've included just some previews of that variance type of visualization to see, if the destination site is still the AGLT2, which is what you're interested in before. Maybe if you've identified a lower throughput, maybe there's a correlation between the packet loss and or the retransmits. And so I've included some previews of that information, which follows the same structure, just on a different page so data doesn't get mixed up. And I've included links at the bottom of each dashboard that allows you to then switch with the same filters over to that dashboard and then look at the packet loss data if you found a strong correlation between packet loss and a lower throughput value. But like I've mentioned, I worked on the OSG toolkit info page in parallel. This is where that filter a couple slides back, this filter here on the left comes in handy. And so not only did I give the OSG filter redesign, I wanted to add some useful features as well. And so I don't want users to have to type in that long string of a filter every time they are interested in the data that they're looking at. And so this is what the old OSG toolkit info page looked like. All the links to the different websites are just strings of text with some descriptions. But I was able to rework and redesign with different color schemes, some previews of what the pages look like with descriptions, as well as labels for different sites that you may not be able to access without the proper information or certificates. But I've also added some new features like I wanted to mention. And so on this main page here, it's just, querying the user who is connected to see if, if they have a general question or they suspect something is going on, they'd be able to click one of these questions, and those questions would then take them to the corresponding dashboards. And so if you suspect a lot of packet loss, as a site administrator, you'd obviously click the packet loss related one, and then that would take you to the packet loss related dashboard. And so all of these questions take you to different dashboards. But some work that I was continuing is, like I mentioned, I don't want to have users have to type in that large string of text, or if the user doesn't necessarily know what hosts or toolkits or sites they might be interested in, I wanted to make it easy for the user to identify which ones might be most relevant to them. And so I was working on a system, and I will continue to work on the system with the SAN group that I've been presenting to every week, that queries Elasticsearch, the data storage base, for all of the hosts that are being stored on there, all of the latitudes and longitudes that correspond with them, the site names, and then we'll compare those to the user's distance, and then give a drop down of all the closest hosts and sites to the user so that it would create an ease of access for users who may not know which hosts or toolkits or sites they're looking for. And so I've created, there's a production value of the OSG Toolkit info page. This is on the developer copy that I've been working on. And so I've inputted test data, and then created systems that grab the user's IP, which I'll quick go through the code in slides after this, and then it creates drop-down menus that represent the closest hosts and sites. And so being able to click those based on which ones are closest to you, and then have links similar to the main page with the questions. But the idea is, if you select one of these hosts, either alphabetically or based on the closest to you, if you select one of these hosts and then answer one of the questions, not only will it take you to the corresponding page for packet loss or throughput, but it will automatically have those filters applied, so the user doesn't even have to worry about fitting the proper syntax for Kibana. They just click the page and automatically have all the information that they'd want on there. And so I created a lot of PHP script to work on the HTML server that's running the OSG Toolkit info page. And so this piece of script just grabs the client's IP and transforms it into a latitude and longitude. And then I've defined a distance formula, as well as the looping code that takes the CSV data. I will put all of the hosts into a CSV file. And so with that CSV file, I'll be able to iterate through every single one of the hosts, no matter the number of hosts, and then calculate the distance and organize all of those hosts by distance. And then creating the dynamic dropdowns. So the way that you'd be able to see all of those hosts based on the distance, creating those dynamic dropdown menus that will allow the users to not only see which ones are closest, but then submit and store those as variables, which I can then use to put into the URLs that will automatically apply those filters. And so the next steps for continuing this work would be to make some more aesthetic and user-friendly changes to the OSG Toolkit info page. For example, putting all of these toolkits in a singular line with different names, and identifying which ways the user will navigate the menu based on how I organize it. But then finishing developing the Python script that will query Elasticsearch for the actual hosts and export them as a CSV, and then setting up a cron job to run that script every couple of days to ensure that the database for the OSG toolkit info page, all of those hosts are keeping updated. And so there won't be any that are being left out. But then also to create more dashboards for more use cases that could be presented, or continue to develop the ones that have already been created. So if anyone approaches me or has any questions about specific types of data that they'd like to see, or any other use cases that they'd be interested in, that's kind of what I want to keep doing, to continue to develop these dashboards. So continuing to work on the dashboards and then finishing the new user-friendly features that will allow people to easily access the data without having to go through a lot of hassle to find it. But that's it for my presentation. So if anyone has any questions.
Anyone?
I just wanted to say that looks like a lot of impressive work. Thanks for the time over the summer, and I hope you also enjoyed doing it.
Yeah, it was very fun. Thank you.
Thank you, Tommy. Next up is David.
Yes, give me 1 second. Let me share my screen. Okay, can everyone see that?
Yes.
Okay. Good morning, everyone, or afternoon. My name is David Liu. I'm going to be presenting my work for the IRIS-HEP as an IRIS-HEP fellow this summer. I worked on ServiceX developing backend tests for it, and my PI for the project was Gordon Watts. So to orient you to the talk, I'm just going to introduce myself briefly. I'm going to discuss my project goal, and then I'm going to give a little bit of motivation. I'm going to discuss what ServiceX is, why people should care about it, and some of the technical terms behind the project that I'm going to be using. And then I'm going to launch into a discussion of my actual work. I'm going to discuss the results from this project over the summer. And then I'm going to discuss what work still needs to be done to build off of what we've already accomplished. So to launch into an introduction about myself real quick, I'm an incoming physics graduate student at the University of Washington. I'm actually beginning graduate school this month and next week. I graduated from Ohio State University December of 2019, and a little bit outside of physics and academia. I enjoy backpacking, rock climbing, and a lot of things that no one can do right now because of the pandemic. On the right, there's some photos of myself, some places that I've been, Great Smoky Mountains, Glacier National Park, and rock climbing somewhere in Ohio. So to talk about the actual project, our goal was to, in the proposal, was to develop a testing suite for ServiceX and to check compatibility between its two backends. I'm happy to report that we were able to do this over the course of the summer. So to discuss what ServiceX actually is, for anyone who may not know, the ServiceX itself is a currently in development data delivery system. It's in beta. It runs on Kubernetes, and it's currently hosted at the University of Chicago at the River Cluster. On the right-hand side, there is a photo of the River Cluster at UChicago. The photo was taken from the Public River website. So what ServiceX is actually designed to do, typically with physicists in experimental particle physics, they're working with data sets that can be enormous in size. Tens to hundreds of terabytes. CERN itself generates petabytes of data. And so downloading data sets to work with, physicists may only need 1 or 2 events in this massive data set. So it becomes very inefficient for them to download the entire thing, sort through it, find what they actually want, and then work with that. ServiceX is designed to allow a physicist to specify what part of a data set they would actually like to work with, and then using this application, download just those portions that they can immediately get into analysis. The service itself is located pretty close to the data, and it's equipped with a very high bandwidth connection to improve efficiency. And so overall, the goal of ServiceX is to reduce the user bandwidth, its download time, and basically allow physicists to immediately jump into doing actual analysis. I mentioned Kubernetes, so I'm just going to briefly go over that as well, because ServiceX is run on it, and it's a pretty important part of the project that I worked on this summer. So Kubernetes itself is an operating system level software. It is a framework that basically controls how containers applications will work and communicate with one another. So Kubernetes is a very cool system that allows us so it automatically manages pretty much everything about these containers, these pods that have to communicate with each other and generally be structured in a very specific way. It automatically deploys containers as needed. It automatically deletes containers as needed, and it makes sure that they're always communicating with each other correctly, and it monitors the entire system's health. It does this by basically being given a chart of what the system should look like, and then it constantly monitors the system, and anytime it seems to be falling out of sync with what this chart it was given looks like, it adjusts it to get back to how it should be. So in this graphic, this is specifically for ServiceX, but I generally give an idea of how this works. So you give this K8 cluster, which is Kubernetes, a deployment command, and it will take a look at this chart that you've given it, and it will adjust the system. It'll roll out everything that it needs to so that the application is actually deployed. And so all of these different components, as I've mentioned, have to communicate with each other in very specific ways. They all need to be there for the actual total application to work. And so all of them are deployed by Kubernetes and monitored automatically, and then you get a ServiceX instance out of this. This is relevant because it actually allows us to deploy ServiceX on pretty much any computer as long as it has a Kubernetes cluster. And so, like, for example, I was actually able to deploy ServiceX instances just using my computer equipped with Docker. Okay, so what does ServiceX actually do? Well, under the hood, I'm just gonna give a brief explanation of what I mean when I say backends and what's going on. So it starts with a user who decides that they want a portion of a data set. So they will submit a query written in what we've called FuncADL, which is a language that is specific for ServiceX, and it allows the user to specify what parts of the data set that they would actually like. So they submit this query to the ServiceX frontend, and ServiceX will take a look at what they want, and it'll grab that data set using the user's own grid credentials. Once it has that data set, it's going to submit it to one of the two backends, and the backends are what do the majority of the work. The backends take this data set, they slim it down, they select the portions that the user is actually interested in, and then they convert them into either awkward arrays or pandas data frames, or they can also return things as Parquet files. And so these backends, there's two of them. One is the uproot backend and one is an XAOD backend. The difference is just the type of files that they take. The uproot backend selects just simple root files, while the XAOD backend is specific for the XAOD type files, which are a data type that's used by Atlas. So these backends, whichever one is relevant, will be given this data set. And the data set will be, as I mentioned, slimmed down. Only the portions will be selected that the user wants. And then the backends will transform them into one of the data types that the user specifies, so like an awkward array. Once the backend has delivered these the columns that the user requested, those are downloaded by the user. And so as far as the user's own bandwidth, they're only ever actually needing to submit the query, and then they just download exactly what they needed. Everything else is handled by ServiceX. So here's an example of FuncADL code actually. I mentioned this is the language that users are able to specify what part of the data set that they would like to work with. And so in this simple example, this one is designed to allow the user to pull this quantity LAR quality from an XAOD file. So it basically just starts with the user specifying in the top line that they are looking at all events, but from all of these events, they want to pull out just the jets. So after the first line, they're only looking at jets. And then the second line, they're saying, okay, well, now we're only interested in jets that have this transverse momenta that's greater than 20 GeV with an eta value of less than 4.5 MeV. Oh, there's a divide by 1,000 there that shouldn't be there. But so once the user has specified these filters, the program is now just looking at these jets that satisfy these quantities. And from there, we tell the program, all right, well, now we just want from these jets that we've narrowed down to only the LAR quality values. And then we want that as an awkward array. And so this simple, like 5 lines of code will allow us to go from a large data set to just the LAR qualities for just the jets that we're interested in. So some issues that we still experience with ServiceX, the uproot and the XAOD backends were designed separately. So there are potential incompatibilities there, which we would like to make sure that they actually are not there. The project itself is still in beta, so it's still being updated constantly. There's constantly new functionalities or changes that are being made. And so we still need to be able to test that the system is still functional after all of these updates. And finally, we want to be able to run continuous integration tests to make sure that all of the system components are still working together. So that is where the testing kit comes in. The testing kit allows us to do all of these. It allows us to test functionality after updates. It allows us to make sure that the backends are compatible, and it makes sure it allows us to constantly check to make sure that the whole system is healthy. Over the course of the summer, that was pretty much what I worked with Gordon on. We were able to, generally, most of my work was done with just Python coding and familiarization with Kubernetes, ServiceX as a whole. So we were able to get a lot of things done aside from the testing as well, or as a result of the testing. For example, we were able to generate a lot of patches for ServiceX for bugs that we just discovered during the course of all of the testing that we were doing. We were also able to make some updates to ServiceX's functionality and capabilities on our own end. Excuse me. So we were able to add additional data types from XAOD files that weren't supported to begin with. And we were also able to implement lazy arrays, which for the awkward arrays, which basically allows us to, instead of loading the entire data set into memory and then working with that, to take only the sections that we need at the moment and then release that memory after we're done working with it. We also improved some documentation for the project. So we wrote new documentation for the FuncADO language. Previously, FuncADO was just undocumented, which made it a little bit harder to work with. And then we also wrote some new demos and examples for ServiceX for new users to take a look at so they can get an idea of how the system functions. But the main thing that we were able to accomplish was that we actually developed this test suite that we set out to originally do. It's driven by PyTest, and we have it functional for both the XAOD and the uproot backends at the moment. And so the tests in this suite are designed to allow us to test the ability for ServiceX to actually retrieve the data accurately. And also, we have some stress tests that are designed so that we can test whether or not ServiceX can handle large numbers of queries at once or very large queries hitting the system all at the same time. We also test that ServiceX is still able to apply those filters. For example, with the previous slide where I had the filters for whether or not we could make sure that we had greater than 20 GeV jets, for example. And then we're also able to look at some timings and whatnot with this testing suite. One of those stress tests, for example, we're able to pull 100 columns of data from a 10 terabyte data set in under 30 minutes, which, as you can imagine, with a 10 terabyte data set, downloading that might take considerably longer than 30 minutes. On the right-hand side here, I have some plots of counts pulled from a Monte Carlo Z to E data set. So we were able to generate these plots in maybe 5 minutes or so. And they have data sets from for lepton information for positron, electron pair production, and the muon pair production for this Monte Carlo simulation. This took us 5 inputs into a Jupyter Lab notebook and 5 minutes, like I said, to generate. So what we have down the line, ultimately, we would like to bundle the testing kit that we've developed with the official release. That's not quite been done yet. We still need to roll the testing kit repo into the official GitHub as well. At the moment, it's still in my private repository. We intend to schedule it to run automatically so that we're not just manually triggering this testing kit after every update, but rather that it's constantly checking the system health on like a weekly basis. And finally, we still need to bundle this kit into a Docker image so that it can be deployed on any system very easily, just with just a couple of commands. At this time, I'd like to thank my PI, Gordon Watts, but I'd also like to thank Mark Weinberg, Ben Galuski, and Mason Profit. All of them were a tremendous help to me over the course of the summer with all the questions that I had and helping me with a lot of the details in ServiceX. And I'd also like to thank actually everyone who I interacted with in IRIS-HEP, which was a very welcoming community, and I felt like I learned a lot from interacting with everyone there. This concludes my talk. I can take questions if anyone has any.
Yeah, can you go back to the slide where you show an example of FuncADL?
Yes.
So, okay, the lambda E, is all the stuff inside the quotation marks just a normal Python lambda function?
So all of the things, yes, all the things inside the quotes, like it can take any Python function. Inside the quotes, I think we were actually working on a way to make it so that you can actually see like color code and whatnot inside there. But yes, so that's why, like, for example, we have the absolute value function in the second line and whatnot. All of these are just lambda functions inside of the program that allow us to use usual Python logic.
But you didn't actually implement this syntax for absolute value. You implemented the select many where select stuff, right?
So yeah, FuncADL was written with the it's an SQL-like language, and so it's the select many, the where, and the select and whatnot. That was written by Mason Profit and Gordon Watts, I believe.
Oh, cool. As for the Kubernetes stuff, do you have to do anything extra for the Kubernetes to get all the extra features like the like container restart, if something breaks or whatever? Do you have to do anything extra for that, or was that already set up?
So to my understanding, Kubernetes, well, it automatically will do all that. You give it an image, like a chart of what the system should look like, and then it just constantly monitors the system, and anytime anything comes out. So like if one of the containers breaks, it automatically restarts it because it's if it's broken, then the system is no longer running like the chart that it was given.
Okay, thank you. Cool project, yeah.
So Vlad, I just wanted to quickly follow up on that slide 9 that David was showing. The stuff that's inside, I'm sorry, it was the FuncADL example. It wasn't slide 9. Yeah, it was slide 8. The stuff that's inside quotes is actually proper Python. That the Python interpreter, we in fact use Python to compile it. And the only reason it's in quotes is because we need the abstract syntax tree. And we don't know how to do that unless it's in quotes. I'm really hoping 3.8, Python 3.8 and 3.9 will have better utilities for extracting that information. But 3.7, we haven't figured out how to do it.
Actually, an interesting hack for them. I don't know if this would actually work, but if you have a function, or say instead of using a lambda function, which you define here, you have a separate function which you define up there or somewhere else, you can write the lambda part, and I think there's a Python function called repr, which just would convert that to a string. Although I'm not sure if that would actually work, but I need to look at that. But
so you're right. Excuse me. There is something that will allow you to do that, but then this 4 or 5 lines of code will explode into something like 20 or 30 lines of code because you need, well, maybe not that many, but you'll still be adding at least 2 or 3 lines per lambda function. right? What with the def and then the lambda
Yeah,
context
there's
and
no
then a
point in
blank
doing
line.
that. Yeah.
Yeah, right. But for more complicated functions, because sometimes you do need to write more complicated things, that's entirely correct. You could do that, and that would work in 3.7. Just, you know, it's like Python went halfway there and then they stopped, and it's incredibly frustrating. Because I would love to. I think all of us would love to get rid of those quotes.
Yeah. Okay. Thank you.
Of course.
Okay, anyone else? Thank you, David.
Oh, I just wanted to say, to just thank David. It's been a lot of fun working with you over this summer, and I've really enjoyed our interactions, and the work you've done has been excellent, and I think it's going to be around for a while.
Thank you. I really appreciated working with you as well. And thank you everyone for your time.
Just wanted to just quickly thank all the fellows and mentors for your work this summer, and look forward to it being used more widely. So thank you all.
Thanks. Take care.
Yeah. Bye.
Thank you.